Can I turn the lights off now?
Huh?
Can I turn the lights off now?
Well, let me just try to think it through. I didn't know. I wanted to wait till you're ready.
Okay. Okay, let's get started. So you have web work due tonight at 5. If you haven't done that yet, you still have till 5 o'clock tonight. I do want to talk about this one briefly. This was number 6. So remember that these problems are translating back and forth between the equation of the circle or the ellipse and the parametric function really comes down to this relationship right here, the Pythagorean identity, right? So that's kind of the key. That's your medium for going from going from parametric functions to equations of circles and ellipses and back is this. You've got this kind of, this is the bridge point. Sine squared theta plus cosine squared theta equals 1. Okay, so you see this equation, you say, okay, I want to write this as a parametric function. So I've got the form something squared plus something squared, but I've got it equal to 4. So I want to make this, first of all, equal to 1. So again, to break this off into a parametric function, or to transition to a parametric function, I'm going to move towards this, right? So what does that mean? I need that 4 to be a 1. So what am I going to do? Divide by 4, right? And then after I divide by 4, I'm going to do 2 steps at once here. After I divide by 4, then I want it to truly look like something squared plus something squared equals 1, and then I'm ready to assign something sine and something cosine, right? So when I divide by 4 and then I group these things together, I'm going to have x minus 5 over what squared? 2. And x minus 6 over what squared? 2. So now I'm ready. So now I've got it looking just like the Pythagorean identity. And I can write my parametric function, or I can make the transition here, right? So I can say x minus 5 over 2. Then what's in parentheses here could be. Now let's see. They're saying they're saying it's going to be cosine, right? Because here cosine equals x minus 5 over 2. But remember last time we talked about how you have all these different choices, right? That first thing that's squared could be cosine, it could be sine, you could be negative sine, negative cosine, right? And then what happens is your starting point is different and your direction is different, right? But here they're telling you that cosine is essentially x minus 5 divided by 2. So then this would be sine. Or it could also be negative sine, right? It just would give you a different. Well, if it were negative sine, it would give you a different direction. So sine or negative sine. So I'll just leave the rest to you. Right here, 2 squared, right? 2 squared. So I did 2 steps at once. I divided by 4 and I tucked it into the square, right? So that again, you're always your center, your focal point is always that equation right there for working your way back and forth between equations in just x and y and the parametric function. Okay, so I'll just leave the rest to you now. Okay, so again, 5 p.m. tonight. If you haven't done that yet, that's due, and then we'll start adding to the homework for next Wednesday, and then again it'll be finalized Monday. Any questions before we start new stuff? Okay, here we go. So we're still talking about parametric functions. So I have this parametric function here. X is t cubed minus 3t squared plus 1. And y is minus 2t to the 4th plus 3t squared minus t plus 4. And so So here we see this kind of we get a graph that's kind of unfamiliar, right? So it's like it looks weird to us because we've been dealing with y as a function of x for so many years in calculus and pre-calculus. So, is it a function? Is it a function? What's the right answer to that? Yes or no? Is it a function? It depends. She got it, right? So it depends on what I'm asking. Is y a function of x? No, right? No, y is not a function of x because given different x values, you could get more than one y, right? So suppose you chose x to be -1. There's clearly more than one y for x equals -1. Are ordered pairs x and y a function of t? That's a function, right? So parametrically, this is a function. Independent, t, dependent, an ordered pair, right? Ordered pair, a set of ordered pairs. So this is a function or not, depending on how you look at it. Okay, so now I'm interested in, I want to pinpoint the t value and ordered pair for the maximum here. So I want to know what's going on here at the local. What's all the information I could want to know about the local maximum there at the top of I call this the anteater function. At the very top of the anteater's head, right? So how are we going to do that? What do you remember from Calc 1 if I want to identify that local maximum? Something's equal to 0, right? What's equal to 0? The derivative. And what derivative do you mean? dy dx? So is dy dx equal to 0 there? Given a small change in x, do you see virtually no change in y at the max for a small change in x? Yeah, right? So this is what you did. But to get dy dx, what do we need? We need y as function of x. Now let's look back at our parametric function here. How about that? How about y as a function of x? You excited about finding that? No, because remember how to do that? Remember what we had to do? We take one of them and solve for t, and then plug it into the other. So here you have a cubic, and here you have a quartic. Okay? So that's not fun. Okay? All right, so we don't want to go there. So we need something else. So we've got x as a function of t and y as a function of t. We're interested in finding the local maximum. dy dx equals 0 is not a viable option because we can't get y as a function of x. And it's not, right? And we said y is not a function of x, right? There is no one equation that's gonna generate this curve because it's not. So we need a new strategy. What else can we use to get the local maximum there? Any ideas? Cody?
You take the derivative of like dx dt, dy dt, and then compare them so you can somehow make it work that d implies dx equals 0.
Okay, so we've got two other derivatives we could talk about. I think I mentioned it last time, dx dt and dy dt. And so which of those two or both would help us pinpoint that local maximum? Is it dx dt or dy dt or both? For a little change in t, we're interested in what? So now we're talking about a little change in t, right? We're saying for a change in t, we want what to be true? The change in y to be 0, right? So that's what we want. So for a little change in t, we want the change in y to be 0. So we can do that. dy dt is easy. It's a polynomial, right? What's dy dt? Negative 8t cubed, 6t minus 1 equals 0. Okay, and so to make this go faster, this is a cubic, and it probably doesn't factor nicely. It probably has, it might even have irrational roots or something like that. So let's just do a graph, just quickly graph this function, and then find the roots of this function. So I'm going to start new. So minus 8t cubed and I'm going to use x because we want it to graph. Was it plus 6x, plus 6t, then minus 1?
Yes.
Is that right? So now the zeros, we're looking for the zeros of this function, right? Because we want that thing to be 0. So where is it 0? So write these down. Here we go. Let's get it a little bit better than that. Write this down. Negative 0.94. I can too, I guess. Yeah. Negative 0.94. Positive 0.17. And positive 0.77. Okay, so we've got those written down. So those are the values of t that make dy dt equal to 0, right? Those are the values of t that make dy dt equal to 0. And what were they again? T equals? Negative 0.94. 0.17, thank you. All right, well, we got 3, so which one is it? So why do we have 3, first of all? Do you see why there is 3 of them? So why are there more than one? dy dt equals 0. So dy dt equals 0 is going to be, in general, in the graph, is going to be when the graph is heading, or the points are horizontal, right? Right? Like so local max or local min, that's when our dy dt is going to be 0. So are there other places like that? Where are they? There's 2 other places, right? Can you see them? There's the one we want. Where's the next one? Right there. So right there at this is a local min, and then there's local max. So for time's sake, so we'd have to identify which one it is. For time's sake, I'm just going to let GC do it for us. Which one was it? The negative 0.93? 94? So there it is. Negative 0.94 is the one we're interested in. And then to get the x and y ordered pair, we would simply do what? Just plug it in. And then it would give us, so for that t, it would give us an x and a y. And then actually GC is telling us there, right there, what it is. 2 points, or negative 2.48. Is that right? Did I wrong correctly? And then 6.0, I can't read it, guys. 6.0, can you read it?
6.093.
09. 03. 29, is that right?
29.
Okay, so we found it. So we got what we needed, and we used dy dt. We said dy dt equals 0 will also be like a local max. Found the t value that made the dy dt equal to 0, and then we could use our function then with that t value to get the ordered pair. Okay, so I'm going to start attendance. I want you to find the far right side tip of the nose of the, and this you can do with algebra. Okay, so you don't need that. So we had to graph this cubic. You won't need that this time. I want you to find the far right side of the set of points, the furthest point to the right. The furthest point to the right on the tip of the anteater's nose. So think about what that would mean and how you would find that. Okay, go. Tristan, what did you do for this? The second t is going to be here at the far right side? Is that right? So what are dy dt equals 0 means what? If dy dt equals 0, what does that mean for points on the graph? For a change in t, what's dy dt equals 0 mean? No change in y. Is that what's happening at the far right side of this? So somewhere over here, that's what we're looking for, right there. So does dy dt equal to 0 there? No. So for change in t, what do we want? Dx dt to be 0, right? We want no change in x for a change in t. So here's the other two for the other two t's for this dy dt were here at this local min and at this local max here. But we're interested in that right there. So dx dt is 0. And what is it? 3t squared minus 6t. And we need that to be 0. So therefore, we should have done 3t times t minus 2. So what t value gives us a dx dt of 0? So there are 2 of them. Should there be 2? So having the graph in front of us, how could we quickly figure out which one it was? Yeah, plug them in and get the ordered pair. We're looking for something around x equals 1 and y equals 4, something around there. And this, I think that's exactly what it is. Is that right? When you put t equals 0 in, you get x equals 1 and y equals 4. So what's going on here? Why is there another one? Is there any other place? So dx dt in general, dx dt equals to 0 is going to pinpoint what kind of place is on the graph. Dx dt equals 0 is going to pinpoint what kind of place on the graph. Isaac. Yeah, so local max and min of x, right? Local max and min of x, which would be like a local right-hand value and a local left-hand value of the curve. So we got this local right-hand value, but we got another one, right? Where is that? Well, it's not in this view. So look what happens if you zoom out some more. See what's happening right here? Do you see where t equals 2 is about? Do you see where that is about? X equals where? Around x equals -3 and y equals negative. So you plug 2 in. You plug 2 in, you get -3 and -18. And so now here we can see that right here. So there's another local, right? Like a local furthest left point, right? Local furthest left point. Did I get it right? Is that right? Okay. Oops, wrong way. Okay, back to our original view here. Okay, so with dy dt and dx dt, we can isolate these places of what? Local max, local min, local max y and local min y, and local max x and local min x. Okay, so we've seen that. All right, now let's take a look at these questions. All right, so hopefully you wrote down the function. Did you write down the function? Let's write it down again. What is it? X equals? Okay, so I got a series of questions for you here. I want you to find the coordinates of the point when t equals 1. That's an easy one. And then without doing any math, I want you to predict so once you isolate or pinpoint that ordered pair for t equals 1, predict if dx dt and dy dt are positive, negative, or 0 when t equals 1. Okay, so don't do any calculations, just predict. Okay, so if dx dt, dy dt are positive, negative, or 0 when t equals 1, and then I think you can do all these, right? So then, again, no math. We're going to do all predicting here. You can just do all conversation and predicting for 2 through 4. No calculations. So no calculations for 2 through 4. All Discussion. Okay, go. I'll keep going on attendance. Okay, what'd you get? T equals 1 is what point? Negative 1, 4. Right there. Okay, what do we think for dx dt? Dx dt, what do we think for that? I heard positive, I heard some negatives. What do you guys think? Adam? Neil, sorry.
Okay. I said negative.
Because?
Just looking at the graph, I saw that x was moving horizontally, was moving negative. So,
If what? What's first, though? To test that, you're saying, I mean, how do you know which way x is moving? Based on what?
the axis.
What's that? Yeah, but x could, right? X could, points could be generated this way or this way. So to say that x, how do we know that x is, dx dt is negative? Bryce, or sorry.
We've seen the function as t gets larger generate, I guess kind of clockwise.
Right. So yeah, we had, these were negative t's up here, right? And we get t equals 0 here at the, over here, t equals 0. Is that what we got for the? So here were our negative t's, then t equals 0, and then our positive t's are here. So when we're looking at thinking about dx dt, we're saying for a small change in t, what does x do? Right when t equals negative 1, what does x do? It decreases, right? The direction of the curve is, like he said, is something like clockwise, right? Something like clockwise. So for a small change in t, x decreases. So dx dt would be negative. And then we can confirm that, right? How we can confirm that? Take your dx dt equation and plug in t equals 1. But I didn't want you to do that. I wanted you to guess here. So what about dy dt? Again, we say for a small change in t, what does y do?
Negative for the same reason.
Spencer?
It's negative for the same reason.
Okay.
Because as t goes from 0 to 1, it's decreasing.
Right, so as t is increasing right here around t equals 1, what is y doing? Points are being generated this way, so y is decreasing, so it's going to be negative again. What about dy dx? Someone said positive up here. Why positive, Maxim?
I mean, because it's going in that direction, so this would be like, I guess, positive, but also if you multiply dx dt by dy dt, negative times negative, you get positive.
Okay, all right, so we can see so there's like both are negative, but how can we just literally translate what dy dx means to see that it's positive? How can we just literally translate that? What do we say? We look at a small change in x, right? For a small change in x, then we look at what's happening for a small change in x, and that would be what? Now going this way, right? A small change in x means increase x a little bit, and what happens to y? Going up. Therefore, greater than 0. Now so Maxim was talking about the fact that these are both negative, right? dx dt and dy dt are negative. And this gets at how we actually can get a way to calculate dy dx. We said that would be impossible to get from a y equals f of x equation, but we can still get dy dx by doing what? How would we combine dy dt and dx dt to get dy dx? Yeah. Neil got it. dy dt divided by dx dt. Do you see how that will be dy dx? And so this is what he's talking about. Since they're both negative, we'd expect dy dx to be positive. All right? And so what would that be? That would be this rational function, right? This rational function. It'd be negative 2t to the 4th. Oh, sorry. We got to take derivative. So the derivative of dy dt is negative 8t cubed plus 6t minus 1 over 3t squared minus 6t. Now, how is this different than the dy dx, the derivative formulas that you've derived in the past? There's a big difference here. What's different about this? So we got dy dx, but how is it majorly different? It's a function of t, right? So it was pretty easy to find it, but now it's a function of t, not a function of x, right? So what would we do? We'd plug, if we plugged 1 into this, we'd get, and so actually let's predict the value. What do you predict that value would be, dy dx, if we actually calculate it? So we know it's positive. We're guessing it. We know it's positive. So like positive a half, positive 1, positive 2, positive 3. Something like what? For a change in x, the change in y is what multiple, right? So back to our same thing we've always talked about. dy equals what? The rate given a change in x. The change in y is that multiple of the change in x. So what do you guess? 1-ish, right? 1-ish for a change in x, you get about the same change in y right there, right? Right in that vicinity, for given a change in x, you get about the same change in y, so that would be about 1. Negative 8, negative 2, negative 3 over negative 3, it's 1, right? So it is exactly 1. If you plugged 1, t equals 1 into this, so at t equals 1, dy dx equals 1. And that's exactly what the graph is showing us there. Okay, what about the second derivative? Predict the second derivative at this point. What would you predict for the second derivative? Remember from Calc 1. So it's how the rate is changing, right? Is the rate increasing or decreasing? Now this is dy dx, so the second derivative with respect to x. So looking at t equals 1, thinking about the rate of change. Is the rate decreasing or increasing as you increase x through there? Does the rate increase or decrease? It's getting less positive. Do you see that? The rate's getting less positive. It's steep, it's heading up sharply here, y values, and then it's 1, and then it's heading up less sharply. So since the rate is decreasing, we would predict that the second derivative, negative, right? And when the rate is decreasing, we get a certain shape of the graph. Remember this from Calc 1? What's the shape of the graph when the rate is decreasing? Remember what that was called? Concave down, right? Concave down. So all through here, the rate is decreasing. So the second derivative is negative. All right, how would we get the second derivative? How are we going to actually get a value for the second derivative? We do the same thing we did for the first derivative. So for the first derivative, what? We took the derivative of y with respect to t, but then to make it dy dx, we divided by dx dt. So we're going to do the exact same thing. We're going to take the derivative of this with respect to t, but then to make it with respect to x, we're going to do what? Divide by. So we're going to take that thing with respect to t, and then just like to get the first derivative, so we took the derivative of y with respect to t, but to make it with respect to x, what do we do? We divide it by dx dt. So we take the second derivative with respect to t, and to make it with respect to x, we're going to no, right now it's with respect to t, we want it with respect to x. And that was the same thing here. It's with respect to t, we want it with respect to x. So we divide it by dx dt. So we're going to divide by dx dt. Same thing, right? So we have the second derivative here with respect to t, and we want it with respect to x. So we just do the same thing we did here, divide by dx dt. All right, so now, What does that mean? It means we're going to have to take this derivative with respect to t and then divide again by dx dt. So what is entailed in finding that derivative with respect to t? Quotient rule, right? Quotient rule. So this whole numerator is going to be the quotient rule. Ready? Low, d high. Ready? Low, d high, negative 24t squared, plus 6, minus high, d low. Will I have room? I'll try. High, d low is what? 6t minus 6.
Wait, I have a question. Why did we not derive them separately? Like, the second derivative of y with respect to x isn't it negative?
No, the second derivative is the derivative of this. Right? The second derivative is the derivative of the first derivative.
Well, that's y with respect to x. We're trying to find y with respect to t.
This is the second derivative of the first derivative of y with respect to x as a function of t. So now to get the second derivative, we're going to take the derivative of that. But we have to do it with respect to t because there's t's, right? But then to make it the second derivative of y with respect to x, then we'll divide by dx dt. See it? So that's low d high minus high d low all over. Low squared. And then that whole thing divided by low again. So then what's going to happen is we're going to get what? We're going to end up getting dx dt cubed, right? We're going to end up getting dx dt cubed because when we divide by low squared, that's going to be dx dt squared in the quotient rule. But then we divide again by dx dt, we're going to get dx dt cubed. I'm not going to rewrite this, but so if I plugged t equals 1 into this is our second derivative of y with respect to x as a function of t. If I plugged 1 into that, what do I expect to get? Negative, because the rate of change is decreasing, concave down, right? So if I plugged 1 into this, t equals 1 into that will be negative. Not going to take the time to do that. Just a lot of number crunching. Okay, questions on that? All that stuff. And a hush. Oh, there is a question. Emma.
So you do all that to find the second derivative with respect to x?
T. Oh yeah, no, second, yes. With respect to x as a function of t, right? So yeah, this is the second derivative. All of this thing that I put a box around. And this is all the numerator, right? This quotient rule is the numerator, and then the denominator is this here. So this bar should be longer, right? This bar should be longer. But yeah, so that's the second derivative of y with respect to x, but as a function of t. Other questions? Okay, so we got 10 minutes. We'll talk about area. So let's talk about area. Last chance on these questions. Okay, so I'm going to look at, say, from so was this t equals -1 was up here somewhere? Where's t equals -1? Right about there? Okay, so let's look at, I'm interested in from t equals -1. I turned that off. It's not letting me turn it off. And that's t equals 1.4, is that 4.5? Yeah, 4.5. All right, before we do that, Let's just do a quick review of when we talked about area toward the beginning of the semester. Remember we made our area function, right? So if this is, say, A. And we were able to write an area function. If this is the function f, the accumulation of area, or assigned area, right? The accumulation of signed area starting from A to any value x. Remember signed area? And what was our, and remember, how did we write the equation for signed area? Accumulation of signed area. Right? So, integral from A to x. Okay, and then the question is, what was the rate function? What was the rate function for signed area? Just the value of f, right? It's the value of f. The rate at which that area increases is the value of f at any given moment. Like the height is the face at which it's growing. So that face there on the left side as that signed area grows is the rate of change. So we said f of t dt, right? Okay, so we're still going to use that. So as we talk about area in parametric functions, this is going to be still be our model. Okay? So, but what's different now? Now we have x is, say, p of t, and y is, say, q of t. Okay? So that's something. This is my parametric function here. X is p of t, y is q of t. Okay? So what we need to do now is we need to, this is a different t. Can I use u's now? Let's use u. So for my original integral, I'm going to change that to u so we don't get confused. So t is our parameter in the parametric function. U now is our dummy variable to set up the accumulation function, right? Accumulation function. Okay, so what is, so we're gonna use this as our model, and we're gonna just rewrite this now in terms of t, the parameter t. So what is f of u? It's the value of the function. And now in parametric, with our parametric equations, x equals p of t, y equals q of t, what is f of u? What is f of u? Was it? No. So when you say it's the rate is the function value, what is that? What the function value is what? In the graph. What's the function value? Thank you, the y value, right? Function value is the y value. So what will, as we transfer into parametric functions here, what will f of u be? The y value will become q of t. It's the y value, right? See that? Okay, now d of u is really a little change in what variable? No, in the original equation here. That's really a little change in what? X, right? So really what we're saying here now is what is dx? What is dx? Okay? So dx now equals what? And so maybe this is the final exam. There's just one question on the final exam. And this is it. Do you pass the course or not? dx equals what? I know Nick knows. Remember our meaning for rate of change, right? Our meaning for rate of change. So if x is p of t, then what is dx? Someone else besides Nick know? I know Nick knows. Kellen.
A small change in PT.
Yeah, that's true. But what does it equal then? The derivative of p with respect to t? That it? Remember? dy equals m dx. Maybe by the last day of class we'll get it. We've been doing it all semester. M means, right, the rate of change means given a little change in your independent, the change in the dependent is m times that much. So now I'm asking for I'm asking for a change in the, now x is dependent, right? In this equation, x equals p of t. X is now the dependent variable. So dx equals the rate times change in independent, dt. So this is dy equals m dx in disguise, right? dy equals m dx. So du then equals p prime of t dt. Oh, we got another variable problem here because we want accumulation with respect to t. So we want the integral to go from, say, t naught to t, and we need a different variable here, right? So in our parametric function, we want the independent variable to be t. So that means we need a different independent variable here. What do you want? V? So in parametric functions, then, this is our area equation, and it comes right, it's modeled right from this, right? The y value times a little change in x. So here's the y value times a little change in x, which is found by the rate of change of x with respect to t times a little change in t. So it follows exactly this model. Y value is the rate, and then times a little change in x. There's our little change in x, which we get from dx is p prime t dt. Okay, so now for this, I'm going from t equals -1 to, say, 1.45. So I'm gonna make this a definite integral. I'm gonna say I'm gonna go from t equals -1 to 1.45 of and this is just what y, this is right, this is y dx, right? Just like in rectangular coordinates, rate of change is y times little change in x. So now my y is my equation for y of t. dx is the rate times little change in t. So the question is, what area or signed area is that going to find? And I'll leave you in suspense because we're out of time.